Okay, so the last time that we were doing module 5, we had stopped at the conformations of ethane, and we were looking at how the eclipsing, where the hydrogen atoms are back to back, and then you take a 60-degree turn between the front two carbons. This is the 60-degree. This is known as the staggered conformation. From 60-degree angle, the hydrogen ion, the starred hydrogens are at a 120-degree angle, and again they are eclipsed. Again, they take a little bit rotation. Now they are at a 180-degree angle, and so on and so forth. And between each eclipsed and staggered conformation, staggered being the lower stability, lower energy, more stability conformation, whereas eclipsed being the higher energy, less stable conformation, we see that the amount of energy between these two conformations was consistently same. And this will be a little different when we will look at butane. And why is that? In ethane, we had seen only torsional strain. Okay, so that is one of the biggest strains that we see in all of the eclipsed conformations. As the conformation moves away from being an eclipse to being a staggered and a completely staggered, maybe, we see that this torsional strain decreases at the staggered view. We count torsional strain at the highest when it is in the eclipsed form. So whenever you will see any eclipsed structures, you have to say that this structure or this conformation has a torsional strain. Now, besides this torsional strain, in butane, we see a steric strain or the spatial strain. This will be present every time you have any groups other than hydrogens and which are very close to each other. And if you remember, I was showing you this particular example right here. When there are two carbons with just hydrogens, when there are two carbons with one methyl group and one hydrogen, and when you have two carbons with two methyl groups. So the steric strain is maximum at this particular example. If we look at the Newman projections, this is a completely staggered compound. This is a completely staggered conformation. It does have some steric strain, whereas this conformation has both the torsional strain because of the eclipsing and the steric strain because of the bulk of these two compounds. And so when we look back, this is the completely eclipsed structure. When the staggered conformation occurs, the first 60-degree angle occurs, we say that this is staggered gauche. Now, gauche is a French word which just means, in French it means a different word, but for most of the English-speaking people, we will just say on our side. So this methyl group is on the side of this group. This methyl group is on the side of this methyl or this bulky group. So whenever we say a staggered gauche, we mean that the bulkiest of the groups from the back carbon and the front carbon are at a 60-degree dihedral angle. Okay, and we can see that in our structure also right here. So this is our eclipse, both groups back to back. As I rotate, let me keep the first one, rotate the back one, you can see that there is this angle. One atom, second atom, third atom, and my fourth atom. These four atoms are in a 60-degree angle. So these two are gauche to each other. What about these two on the same carbon? We are not looking at the same carbon groups. We are looking at the groups of the front carbon and at the back carbon. And so this is why we see the difference in energies in the butane, which gives rise to more conformational isomers. And so if we start at the most eclipsed butane, where both the methyl groups are back to back or energy cost is very high, both torsional and steric strain exist. After 60 degrees, only the torsional strain is removed. You still have the steric strain. Okay. Look at this particular staggered form. After one more round, this is still eclipse, energy is 16, somewhere 16. But next time this group rotates, it is now at the maximum possible distance or 180 degrees from our original group. So whenever your bulkiest of the groups are at the opposite ends or in the anti-peri site, this will be known as the staggered anti-conformation. Okay, so there is this word called syn. Syn means same side. Anti means opposite side. Okay. So this 16 kilojoules per mole instead of the maximum possible 20 kilojoules per mole exists because of this small difference. And this 4 kilojoules versus the 0 kilojoules exists because of the removal of this steric strain also. Okay. So whenever there is no torsional and no steric strain, that would be the most stable conformation. In your exam, you may be given a question. Your question would be draw the most stable staggered form for a material, for a compound, or draw the most stable eclipsed conformation. So out of all of these four eclipsed conformations, these two are very similar, exactly similar actually, same energy. And so you can draw either of those if you are asked to draw the most stable eclipsed butane, which is the most or higher energy staggered butane. Either of these two will be the high energy staggered conformation. So read the question. You may not always get the lowest energy to draw or the most stable one to draw. You may be asked the least stable. You may also be asked the second least stable. So you have to decide where will you see most torsional strain, where will you see more steric strain. That is where you will get your instability or higher energy, as you will say. Okay, so let's look at these structures right here. Can you all see my page?
Yep.
Go ahead and start copying these structures. So on my first carbon, I have a pH, a Br, and a H. On my back carbon, I have a staggered conformation with hydrogen, and methyl. For this particular structure, I'm going to change a little bit, just a little bit. So I just want to tell you these are constitutional isomers that I am making. And I'm making the Newman projection of the constitutional isomers. So the red depicts my back groups. Right. H, BR, H. So you will be given only two kinds of conformations, the staggered and the eclipsed. So please make sure that you understand and are able to recognize which is the eclipsed version, which is your staggered version. And also try to understand what would be your first carbon, which will be your second carbon. Have you all copied this? These four structures, we can label them A, B, C, and a D. So if you look at all of this, which of these will have the lowest of energy? Lowest energy would mean no other energy interference, no torsional strain, no steric strain. Even if it is not possible, you should try to have minimal amount of torsional and steric strain. So let's look at all of this. Do you see the steric strain, the steric strain, the steric strain, the steric and torsional strain here? So this molecule has both torsional and steric. All of these just have steric. So if we had an answer, we had to answer the highest energy, we would have chosen this one. So for lowest energy, D is out of question. Then we look at all of our other constitutional isomers. Now, on the first carbon, which is the bulkiest of the group? On this structure, the bulkiest group is this phenyl ring. At the back carbon, which is the bulkiest of the group, this right here. So the bulkiest of the groups are staggered gauche to each other. Let's look at this carbon. On this carbon, my bulkiest of the group is phenyl. On the back carbon, my bulkiest of the group is Br. So my bulkiest of the groups are what here? Staggered, anti. So anybody had a question? Oh. On my structure C, on my front carbon, my bulkiest of the groups is Br. And on my back carbon, the bulkiest of the groups is a pH. And so my bulkiest groups are staggered gauche. And from our information from a few minutes ago, butane, when it is gauche, will have a higher energy. Butane, when it is anti, has the lowest energy. So among all of these four structures, the lowest energy will be for our structure B. Why? Because both the bulkiest of the groups from the front carbon and the back carbon are anti to each other. Of course, there are other groups hanging out here or bothering them with some steric interference. But then again, we just had to look out for the structure with the lowest energy, the most stable. So highest energy, lowest energy. We just have to do with what we already have. So far we have looked at our torsional strain, which is bonds when they are not staggered, eclipsing, which causes greater electron-electron repulsions. We've also looked at the steric or the or the non-bonded or the van der Waal strain. So either of these names can be used for the strain. When two groups who want to occupy the same space and may bump into each other. The third kind of strain that we will look at is the angle strain. An angle strain arises in our cyclic compounds. So remember your hybridization at this point. And let's just look at sp3. What is the bond angle associated with sp3 atoms? 109.5. But for our ease or convenience, we'll just look at 109. Now, remembering your high school geometry also, what is the bond angle in an triangle or equilateral triangle where all the sides are equal? Within the triangle, you have 60 degrees. Okay, that is in an equilateral triangle. For a right-handed triangle, what is the maximum number or angle that you have? 90 degrees. What about cyclopentane? Oops, cyclopentane. What do you think is the angle right here? Definitely not 109. Not 109, not 109. So if you look in all of our structure, which we are going to see in a few minutes, a cyclopropane, a cyclobutane, a cyclopentane, the bond angles are compressed or sometimes extended in so much that the bond angle is far from what the actual bond angle that atom requires or from its ideal value. So all that compression or deviation from the actual value causes the angle strain. So three strains that we have looked at, we will look at them again in our cyclic molecules. So non-bonded is just steric and torsional is what we have looked at for the eclipsed. So angle, torsional, non-bonded. There is a bond strain also that is present, but we will rarely use it. Generally in IR, when you have the IR samples that we prepare, IR samples, where we see compression or expansion of bonds, but we cannot show those compressions or expansions in drawings. So for your choices, you will only be limited to discuss or decide among these three types of strains only. You don't have to worry about the bond strain. Any questions so far before we start jumping to cyclopropane? Okay, so as I was showing you the bond angle within the triangle of the cyclopropane, and cyclopropane is the smallest ring that can form. because you need at least 3 dots to make a ring. This bond angle is somewhat 60 degrees, and imagine it getting compressed from 109 to 60 degrees. So in the smallest cyclic ring, which is flat and planar, we see a lot of angle strain. And we also see that each and every hydrogen is eclipsing the other. So there is this one set, this one set. There is this one set, eclipsing each other. This set, this set. So 6 sets of eclipsed hydrogen interactions. So what all do we have here? We have a torsional strain, we have the angle strain, and the steric strain. Is there a steric strain here? Not here, because all of these are hydrogens. If we had a bulkier group, so let's say I had CH3, CH3 here, and all of them were hydrogens. Now you will say that there is an angle strain, there is a torsional strain, and there is steric strain also present in this molecule. Any questions? So cyclobutane. Cyclobutane is also not far from being a strainful molecule. In cyclopropane, the strain energy is 115. What does that mean? It means it's quite unstable. It is ready to be reacted and come back to its more stable form. So if you compare cyclopropane with just propane, who will be more reactive? The cyclopropane, because of all the strain that is associated with it. Whereas propane, just the simple linear chain propane, will be very, very stable and very happy with where it is. Cyclobutane has a little less strain than cyclopropane because it puckers. Okay, why does this puckering occurs? If our cyclobutane was a completely flat structure, what would be the bond angle here? 90 degree. All of your hydrogens would still be eclipsing. However, in cyclobutane, this strain gets elevated because of this puckering. So it's deviating from its flat planar nature. It is getting a puckered shape. The only problem it is that from 90, it reduces to 88. The bond angle even further reduces. Okay, it's not very helpful for angle strain, but now it has a little less torsional strain. So that eclipsing is between these two sets and these two sets. 1, 2, 3, and 4. So only 4 sets of hydrogen eclipsing will be seen. So if we go back here, cyclopropane had 6 sets of hydrogen eclipsing, but cyclobutane has only 4. So there are advantages and there are disadvantages also for everything. Okay. Cyclopentane. Now in cyclopentane, your strain is even much less than the cyclobutane. It is also not planar and it puckers like an envelope, and that increases its angle strain. Fortunately, not as much as cyclobutane. So you see there is this planar part and then a raised carbon, which takes the conformation of an envelope. It still has some torsional strain, but not as much if it were a flat molecule where all of these hydrogen pairs would be straining. So then we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, at least 10 hydrogen-hydrogen interactions. But now it is a little less. So angle strain and torsional strain, that's what we are seeing in all of these cycloalkanes. But we are also seeing that the strain energy is reducing as the number of carbons is increasing. And that is what brings us to cyclohexane. And most of our reactions, or most of your conformational chemistry, will be dependent on cyclohexane. There is no strain, no torsional strain, no angle strain in cyclohexane. All the angles within the structure are also 109. All bonds are staggered. What does that mean? No torsional strain, no angle strain. Okay. It is also not a flat planar structure, but this conformation is something that we need to be able to identify and be able to draw carefully. There are other cyclohexane conformations which are not very important. So I will not be asking you any of these, but if you look back at this conformation, this is known as the chair. So how does it look like a chair? Let's draw two parallel lines. So these are those two parallel lines. One of the carbons is going up, one of the carbon is going up. And if there was a person, he could sit or she could sit like this. So this conformation is known as a chair conformation. We just look at it in a slanted manner. So I just twist or turn it a little bit and I will see a structure like this. I can also draw the flipped structure. So just like I had drawn these two, I'm going to draw these two right here. In here, I had drawn one carbon going up on this end. Here, I will draw the other carbon going up like this. Here, I had drawn the other carbon going down like this. I can draw my other carbon going down like this. So if I rotate the structure a little bit, this is what my structure would look like. I mean, the way I draw it, of course, it took practice, but this is how I initially learned how to draw my chair conformation, this chair conformation of cyclohexane. Oops. So in the boat conformation, we see there is a little bit of strain present. Not a lot, but still there is. There is these 4 carbons which are lying in the plane. And then both the carbons, instead of going down, are pointing up. Pointing up, pointing up. And from this cyclohexane, we see flagpole interactions. So just like on the top of the castle, you would plant a flag. These flags are again V-shaped. Why are they V-shaped? Remember, this carbon right here is a tetrahedral. This carbon right here is a tetrahedral. And this conformation or this projection which you are seeing is known as a Haworth projection. The frontal carbons or bonds are wedged which indicates that across this plane, half of the molecule is going at the back. Half of the molecule is going at the back. So if these two bonds, this bond is coming in the front, this bond is going at the back, these two are your planar p bonds, and from this carbon, one bond is coming in the front, one bond is going at the back. But these flagpole groups can interact, eclipsing each other and hence causing torsional strain. If there were bigger groups, for example, if there were CH3s and ethyl groups, if they would also cause non-bonded or steric strain. Remember, steric, non-bonded, van der Waals, space strains all mean the same thing, that somebody's trying to occupy someone else's position or space. The twist is a little bit more stable than the boat conformation because of the puckering that we see here. So the twist or the puckering of this flat area causes these dipoles to be partially eclipsed, not completely eclipsed, just partially eclipsed. Okay, so these half chair conformations, for example, this conformation, carbon-carbon, is more energetic than the regular chair. So twist, so chair is the most stable, twist chair, twist boat is the next stable, boat, and then half chair. Most energetic, least energetic. Most stable, least stable. So looking at your cyclohexane, we also need to be able to identify the various locations which your cyclohexane will have. And this is just the side view or the Newman projection that we can see from two of the carbons of the ring. If you look at that, there is absolutely no eclipsing. There is only staggering between this carbon right here and then this carbon which is at the back. So there are two carbons. Okay. On each carbon, besides the two bonds that are involved in the ring, you will also see an axial bond and an equatorial bond. Fortunately, the axial bonds are always perpendicular, whereas the equatorial bonds are always drawn away from your ring. So wherever your ring is, you will draw your axial bonds away from it. Okay. So let's try to draw our benzene ring. Please make sure that you all need to understand how these rings are drawn. First, I have to draw my two parallel lines, then my two lines above and two lines below. Okay, and I will translate it to something like this. Now you should be able to identify which of the carbons are pointing up. This carbon is pointing up, this carbon is pointing up. What about this carbon? This is pointing down. This carbon is pointing up. Now, there is a particular relationship. 1, 2, 3, 4, 5, 6. So 1, 3, and 5 carbons are pointing up, whereas 2, 4, and 6, these carbons are pointing down. Now, how did I do the 1, 2, 3, 4, 5, 6? You can start from any carbon as long as you know which carbons are pointing up and which carbons are pointing down. So draw your structure first in chair conformation, and then figure out carbons pointing up, carbons pointing down. Why is that important? Because we have to draw our axial bonds first. And if something else works for you, that's completely fine and great. But this is what I have been doing. So from all the carbons that are pointing up, and I hope all of you are drawing with me, you will draw axial bonds perpendicular facing up, perpendicular facing up, perpendicular facing up. On the other hand, from my carbons pointing downwards, I will point an axial facing down, perpendicularly down, perpendicularly down. Now with practice, you will also start to make these bonds in equal lengths. So you will stop your hard axial bond here and not go down to the bottom of the page. So approximately the lengths of all these bonds that I have drawn are very same. So what I have are axial bonds. Now remembering your zigzag. If you remember your zigzag, and if I have to draw my two other bonds from this carbon, I would just draw a V facing upwards. That's the exact same thing you have to do. If you look at this carbon, there is already a V right here. And you have started to make the other V facing up. So where will the other bond go? The other bond will go away and down. In my this other V, my this bond was axial bond, which is going up. And my other fourth bond from this carbon will also make a V, but going down. In this carbon, I have these two bonds already in the ring. One bond, which is going to make part or will be part of my new V, is facing down. Where will my other fourth bond go? It will like to make a V, and so it will go up. Who doesn't understand what I'm trying to make here? So this is my axial bond. This is now my equatorial bond. All of my equatorial bonds I'm going to make in my black pen. Any questions? Looking at this, two bonds are already made. My other V should be one V bond is going down. My equatorial bond will be another V, either in this direction or I can make in this direction also, but just to make it easier for all of us to see. So this is a V that I have made with my axial and equatorial bond. Remember, axial will always point perpendicularly either upwards or downwards. They will be upwards alternatively. They will be downwards alternatively. And my equatorial bonds will be facing away from the ring and in the opposite direction of the axial. For example, in this carbon, axial is going down, my equatorial is going up. Similarly, on this carbon, I already have these two as V. My other will be this V. So this red bond and this black bond are making a V of themselves. This carbon already has two bonds, one bond going down, equatorial will go up and away. On this carbon, I already have these two bonds, one bond from this V, the equatorial will go down and away. So knowing where to draw your axial and equatorial will help you plant if your structure is going to be cis or if your structure is going to be trans. Also, whenever you're looking at alkenes and you're looking at rings, you have to give them a cis or trans geometrical isomer. So the ring flip is the way cyclohexanes have conformations. And I'm not sure how many of you have a model right now, but I wanted to show you this model right here. So this is my cyclohexane, right? These are my 4 planar carbons. One of the bonds is going up, and then one of the carbons is going down. And I can draw it like this, or I can just flip my bonds. The one which was on top are now at the bottom, and the one which was at the bottom is now at the top. This is the only conformation that can occur because this is a locked system. I cannot rotate across a single bond. So this is my single bond. I cannot rotate across this. It'll break the molecule. So the only way the cyclohexane will do conformations is by the flip of your structure. So in the flip, all the carbons that are pointing upwards go down, and all the carbons who are pointing downwards go up. How does that help us? So if you remember this particular structure that I was trying to make, let me remake it here. And I will just draw the flip first. Let me start to count. This is my carbon 1, 2, 3, 4, 5, 6. I have to make sure that now in my flipped version, the carbon 1 points down. And my carbon 2 points up. Carbon 3 down, carbon 4 up. So this is my carbon 1 and this is my carbon 1, and I will label them again. 2, 3, 4, 5, 6. Now I will go only with one of these. On carbon 3, which is going upwards, I will draw my axial bond upwards, my equatorial bond in a V shape going away from the ring because axial was going upwards, my equatorial will go downwards. What would happen on carbon 3 right here? So this is 1, 2, 3. What is happening on carbon 3? My equatorial is now going down and my axial or my equatorial will be like that. So what was on axial is now on equatorial, and what was on equatorial is now on axial. So did I change the position of my groups? I did not change the relative positioning of my groups. The stereo center stays the same. The only thing that has happened is the axial has now become equatorial. The axial was facing upwards. The equatorial is also still facing upwards. Any questions from this part? Any questions? Do you all understand what is the axial location? What is the equatorial location? So the first thing that you have to do is you should be able to recognize if your structure has an axial location or an equatorial location. So all of you draw this structure now. On this carbon, I'm going to draw this bond just for all of us to see. And on this carbon, I'm going to draw a bond, something like this. And I want all of you to draw the structure. You don't have to tell it to me right now, but I want you to think about it. Out of these two, so one is a chlorine, one is a methyl. I hope all of you have drawn the structure. Is there anyone who has not drawn the structure yet? Okay. I'm assuming everybody's pointed no, so everybody knows. Out of these two structures, which of these have been placed on an axial side? Which of these has been placed on an equatorial side? And I'm going to open up the poll now. You will have 1 minute to complete this poll. So again, I'm repeating the question. For the compound shown in this box, which of the groups is a axial and which of the groups is a equatorial? So remember, recognizing your positions of your axial and equatorial is very important, especially when the ring flips or the other conformation is seen. Always focus on one carbon. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay. And most of you are right. This is very exciting. So all of the 8 students who have answered this are saying that chlorine is in the equatorial position, whereas methyl is in the axial position. And that is the correct answer. Very good. And so recognizing these positions are very important. So what I'm showing you right now is a chair conformation. From this chair conformation, we can also make our simple flat structure. How would we depict this in a wedge and a dash? Remember a few on last week when we were looking at the different projections, I showed you the wedge and dash, the sideways, the partial side as a seam sawhorse projection, and then the Newman projection. And now we're looking at the chair conformations. We should be able to draw from one projection to the other. So looking at the structure, is the chlorine and the CH3 both in the same plane or in opposite planes? So if you look at this chlorine is going down. So I will choose any carbon. I will choose this carbon and I will show my chlorine going down. So this is carbon 1, this is carbon 2, oops, 2, 3, 4, 2, 3, 4. Okay. So from both the sides, carbon will be 4. So this is 1 and 4 carbons. So carbon 1, 2, 3, 4. My methyl will be placed on this particular carbon. Where will this methyl group be? On the same side, on the syn side as this chlorine. Why? Chlorine is going down, methyl is also going down. Do you see that? So both of these Newman projections indicate that chlorine and methyl are cis to each other. So whenever we will write the name of the structure, this is a chloro, this is a methyl, who will be named first because they have same priorities. I will go with number 1 here. Where is my lowest locant? From either side, I will have the same situation. So I have 1 chloro, 4 methyl, cyclohexane, and I will make sure that I label the word cis with it. So you have to know that all the carbons pointing to a different direction, the groups on all the bonds are still the same. Okay, so in here, hydrogen and methyl are relatively in the same orientation. Hydrogen is going up here, hydrogen is still going up here. Methyl is going down here, methyl is still going down here. Okay. Now, besides this, and we need to be able to recognize what is a cis-trans combination. So from one view to the other, make sure you do not change the constitutional or the connectivity of the isomer, and keep the stereo centers also exactly the same. So looking back at this, when you have to decide if a molecule in the chair conformation is a cis or trans, always remember that a group at carbon 1 and a group on carbon 2, if they are both axial to each other, so axial, axial, how would that look like? The axial from this carbon goes up, axial from this carbon goes down. Where do you think these groups are in relation to each other? Are they cis or are they trans? So carbon 1, carbon 2, carbon 1, carbon 2, groups are axial to each other. And that means they are going to be trans. Any questions from this part? Because if you memorize this relation, you will be able to memorize all the other relations as well. So 1, 2, axial, axial are trans. When you will flip it, both of these axial will become equatorial, right? But do you think we will change the stereo centers, or will we change the orientations at that point? No, they will still stay trans. So let me show you. If there was an equatorial here, it will face upwards. If there was an equatorial here, it will point downwards. So now this group going upwards, this group going downwards, still in the trans orientation. Now 1, 2 and 1, 4 have exact same orientations. If a group, so this is 1, 2, 3, 4, axial, axial. This group is trans to this group. So my 1, 4 axial, axial is also trans. My 1, 4 equatorial, equatorial will also be trans. What about my 1, 2 axial equatorial combination? When you will have an axial equatorial combination, and let's say 1, 2 axial equatorial, what is happening? Both my groups are going upwards. They are facing upwards. So it will be exact opposite of 1, 2 axial, axial. What will be the exact opposite of 1, 2 axial equatorial or equatorial axial? This is still cis. 1, 2 axial equatorial, equatorial axial, 1, 4, 1, 4 axial equatorial, equatorial axial. all of these will be cis. Just because, you know, they are not 1,2 axial trans. But what about 1,3? 1,3 will also be opposite of 1,2 axial. If you look back here and I try to make 1, 2, 3, axial, both groups on the same side, opposite to that of what has happened with 1,2. 1,3 axial is trans, 1,3 equatorial is cis. So 1,3 axial cis, 1,3 equatorial cis. 1,3 axial equatorial. Anybody? What would happen to 1,3 axial equatorial? Elizabeth Chapman, are you here? Are you following what the relationships we are talking about? Okay.
It'll be cis.
So 1,3 axial is cis. 1,3 equatorial is cis. What would happen if I have a 1,3 axial equatorial? What would happen now? Are they facing the same direction or opposite directions?
Opposite.
Opposite, very good. And so what would be the relationship here? It would be trans. What about 1,3 equatorial axial? What would happen to them? They are exactly the same, right? I'm just replaced or switched the locations here. So what would happen to 1,3 equatorial axial? Would it be cis or would it be trans?
Trans.
Very good. Very good, Elizabeth. Good job. And so let's keep these rules for a couple of more minutes so you can all see that. So I'm going to draw a few structures here. Looking at this structure, CH2, CH3, CH3. What is the relationship between these two groups? I'm not asking you the name, just the relationship. Remember, whenever you will have an alkene or you have a ring, you have to give the cis trans or the geometrical isomer nomenclature to them. So is this cis or is this trans? Kiera Weston, what is the relationship between these two groups, cis or trans?
Trans?
It is trans. Very good, Kiera. Thank you. So the ethyl group has a wedge. It means it's coming out, whereas the methyl is going down. So both of them are in the opposite planes. If I look in my chair conformation and I draw both of them in my axial versions, let's say I draw this in my axial version and I draw this in my axial version, this is what it would look like. So what has happened? Trans in axial position. 1, 2. Can you all see this? So they are 1 and 2, 1 and 2. So on carbon 1, it is in axial position. Carbon 2 is also in axial position. They are trans to each other. What about if I had drawn them like this? Ethyl, methyl. This is still trans, right? But now I have drawn them equatorial. So 1, 2 equatorial. is also trans. Okay. So one of the questions that you will see is that if you're given a name of a structure, you will have to draw the chair conformation. So there are a few rules that you need to remember. So let's talk about the stability of cyclohexanes. So make sure to memorize this rule and to be able to derive the other rules from it. So following the cyclohexane stability, always remember that do not change the constitutional or the connecting ability, constitutional view or stereocenter. What is the other group behind this ethyl? There is a hydrogen here. What is the other group coming out of this carbon? It is the hydrogen. You cannot miss them. You cannot switch the locations of hydrogen and ethyl and hydrogen and methyl. That's what the stereocenter is. When you're asked to draw any molecule, please remember to place the bulkier group on equatorial site first. Also remember not to have any 1,3 diaxial interactions. Let me quickly show you what are these 1,3 diaxial interactions. So this is carbon 1, 2, 3. 1, 2, 3. So relative to this carbon is number 3. Relative to this carbon can also be number 3. And 1, 2, 3. Relative to each other, these carbons are also on the 1, 3 location site. And as we had looked at earlier, alternative carbons have their axial groups on the same site. If there are hydrogens, it's completely fine. But as soon as you will have bigger groups or bulkier groups on the axial sites, they will start to have steric strain. Okay? So even though it's just gauche, the staggered gauche, it is still a little bit significant. So remember we had also looked at the flagpole interactions. Similarly, these are space interactions. These are also space interactions. To just avoid these diaxial interactions, and if you have to, you will have to draw the the higher energy or the lower stability molecules of these conformations, then you might have a group like this, but otherwise avoid placing the 1,3 diaxial interactions. So after you have placed the bulkier group on the equatorial site, the other group in a di-substituted cyclohexane will be based on cis or trans relationship. And let's do an example for that. Okay, let's see that you have to draw a 1-seg-butyl, 2-isopropyl cyclohexane. So following this rule, first of all, let's make our cyclic ring. Okay. Where are the two locations? We have a carbon 1 and a carbon 2. And before I actually figure out which is my bulky group, which is my less bulky group, let me draw my axial and equatorial bonds. So this carbon is facing up. I'm going to make my axial bond go up. This is my carbon 2, where my axial bond has to go at the back, at the bottom. My equatorial will be going away. So there is my new V here. And my equatorial will go going up and away, making my new V right here. So I can locate my equatorial sites and my axial sites. Now I have to decide. Out of the sec-butyl, remember when you're naming, you only look at special alphabets. Iso and neo are part of your alphabets. Sec and tersh, they are not part of your alphabetical order when you're writing the names. So between isopropyl and your sec-butyl, which is the bulkier group? Anybody? So propyl has, sorry, yes, sec-butyl, very good. Why? Because propyl has only 3 carbons. Butyl has 4 carbons. So where am I going to place my sec-butyl? I have to place it on the equatorial site. So on my equatorial site, I will have to place a group like this, where the attachment will be from this carbon. So this carbon right here, and then 1 carbon, 2 carbon, 3 carbon, 4 carbon. This is my sec-butyl. On my other carbon, and I will label this as hydrogen. On my other carbon, I have to place my isopropyl. Should I just go ahead and place it on the equatorial site? Or should I wait to see the relationship between these two guys? I have to look at the relationship between these two. So this is trans. Where should I put? On the equatorial or the axial of the carbon 2?
Equatorial.
So if I go back, I need a equatorial on 1. Where should the other group on the carbon 2 should be so that I get a trans? It has to be equatorial. Very good, Nelson. So what does my isopropyl look like? CH3, CH, CH3. This is where the attachment is from. I just have to do this. And this will be my hydrogen. Yeah. This is my low energy conformation. What would be my high energy conformation be? This will be my high energy conformation. Axial, axial. Why? Because there will be 1, 3 diaxial interactions here. There will be 1, 3 diaxial interactions here also. So when I place my bulky groups on my first bulky group has to be on the equatorial side. What instead of trans, I had a cis 1 sec-butyl, 2 isopropyl, cyclohexane. Exactly same ring. I will draw my axial bonds first, then my equatorial bonds. I want to place my butyl, sec-butyl on the equatorial site. Where will I now place my isopropyl when I want cis? Because I want cis on 1, 2, I have to make sure that the other group is on the axial site. Why? Because I have already placed one of my groups on the equatorial site. Now for my cis, my isopropyl has to be on the axial location. Not very ideal, but still low energy. Low energy from what? This is my low energy conformation. If I had a system like this. This is also cis, exactly same, right? But my bulky group is now in the axial position, which would mean more steric problems. So this will be high energy conformation. Any questions so far? So drawing out your structures is also very important for your this particular module. So if you look on this slide, I still have another Haworth projection. Haworth projections will indicate that these bonds are coming out of the plane while these bonds are going at the back. So if you look at this carbon, it is much easy for you to see. But if you're at this carbon, how would you see now? How would you see what are the projections? This is definitely your wedge, and this will become your dashed. Both of these will be your planar structures. And why do I emphasize on this? We are going to look at these Haworth projections at your cyclic conformations again in modules 6. So if you look, both your bulky groups of these carbons are on the same side, just like when you have a alkene and both priority groups are on the same side. We call them as cis if the priority groups are exactly the same. But if priority groups are not the same on the alkene, what do we call them then? E or Z? Z. Why? Just think of them zooming together on the same side. But for the rings, we will just focus on cis and trans. So the priority groups are opposite to the plane, and hence we say it is a trans. Okay, remember, in the ring, your conformations cannot be rotated by just one single rotation. So this is just a small chart that all of you can look at when you have to think about these stereoisomers. We have looked at the constitutional isomers, we have looked at the geometrical isomers, and we have also looked at the conformational isomers. For your exam 1, which is on Wednesday, we will not be having module 5, but you will be seeing nomenclature, and you need to understand the cis, trans, and the EZ kind of versions. And this is just another way of writing out the structures when you have a cyclohexane and you have to give the relationship properly. Okay, remember the lower energy out of these two, which will be, in this case, both your groups are exactly the same. One is axial, one is equatorial, one is axial, one is equatorial. And so there is no energy difference between these two. Okay. Any questions?